Good morning, everybody. So welcome to the morning session of the day 3 of Dsfd 2024. So I'm very happy to introduce the invited speaker of today's morning, Pudong Chen. Well, Pudong Chen doesn't need introduction. The reason to say that he is one of the pioneers of the subject which majority of us enjoy here these days. So we are somehow here because of him. So he was the founding person behind the famous Exact Corporation, which was the pioneer in industrial applications of the Lewis Boson method, as of course everybody knows. I have to say that. And I'm very happy that you make it to Zurich these days. And Pudong is going to present a talk on the title on kinetic theory and representation of average dynamics of turbulence of dynamics of turbulence. So it is a little bit convoluted.
Sorry
the
for my
subject
English.
is convoluted, so the title has to be convoluted. So, Pudong?
Thanks, Ilya. I'm honored to present to this audience at ITAHA. And I really thank the Dsfd and the local community for me to participate in this event. And I feel, even though I have given hundreds of talks, but I feel a bit still nervous and to present each time, including this one. So as the title said, it's convoluted, but since I guess I'm one of the few presenters in this conference coming from the industry. So I will. Didn't work. Sorry. Kind of frozen. So I'll try to start with some video clips that shows the importance of
Now it should work.
Okay, thank you. Show some importance of the CFD in real world engineering applications. The first video is really actually a commercial advertisement from my company, Dassault Systems, but ignore the commercial part of it, but it just give you a flavor of how the CFD transform the industrial development process. And then I will try to relate that to more of some important questions in CFD, not just a computational method, but also have to incorporate appropriate physics modeling in order to really make the application viable. And so that will turn into something more fundamental that I have been thinking about, that not just only recently, but through some years, and has made some progress, but is not, I wouldn't say it's the final thing. A lot of things can be done. So start with a clip.
The automotive industry is undergoing disruptive changes. Vehicle electrification, autonomy, and connectivity are required in order to meet customer demand, and new, more stringent regulatory requirements. At the same time, a broader, more aggressive competitive competitive landscape and consumer style-based buying systems require automakers to create more visually appealing designs in ever slower development. Vehicle size greatly impacts aerodynamic behavior, which in turn influences the performance and regulatory compliance targets that engineering teams are mandated to meet for range, efficiency, and handling. Traditional development and testing processes that rely heavily on physical models and wind tunnels are not able to keep up with this changing environment. Full vehicle prototypes are expensive.
These are all virtual.
Wind tunnel time is a scarce and expensive resource, and reliance on it can lead to bottlenecks in the development process. These factors increase cost and add risk to meeting on-time product launch. On top of this, the number of vehicle variants required for testing has greatly increased, further stressing testing resources. With the penalties of not meeting updated regulatory requirements potentially reaching billions of dollars, manufacturers need to find more efficient aerodynamic assessment and compliance solutions. With Dsfd vehicle aerodynamics industry process, you now have the ability to address all of these with confidence. Beginning in the concept phase, designers are able to get rapid, early feedback on how their shapes will perform and collaborate with engineers to ensure performance requirements can be met, leading to reduced design coverage. This process is expedited with design, an intuitive and collaborative interface to quickly visualize results and provide simple guidance on how to improve performance. Moving to the detailed design phase, engineers are able to use fully detailed geometry, eliminating time-consuming and accuracy-reducing geometry simplification. They optimize performance of vehicle designs with best-in-class accuracy using a transient lattice-Boltzmann-based power flow solver. Since aerodynamic performance is not the only requirement for design guide enables collaboration with other engineering teams to balance competing objectives for wind noise, water management, and engine cooling. Once all performance objectives are met, engineering teams complete the transition of digital regulatory compliance tests, ensuring they meet certification requirements across all vehicle variants with the accuracy and geometry fidelity needed. With Simulia's vehicle aerodynamics industry process, we will enable innovative design, prevent late-stage failures.
All right, I have to, go a little faster. So this is a real example that I think worth mention that we have been collaborating with Tesla, and Tesla does not use real wind tunnel. It really believes in virtual wind tunnel. So we are the collaborator with them, and they started at first with a conceptual design, and that turned out to be the drag value is too high. And then after iteration of the shape, and then we were able to reduce it significant to the final like 0.24 CD. And that is one of the lowest sedans in the world in terms of CD. And that is very important for Tesla to be a successful company and only use digital experiment. So I just want to mention that. So now let me quickly summarize my understanding through the years of why lattice Boltzmann. First, lattice Boltzmann recovers Navier-Stokes under certain well-known conditions. And that is do not need too much of explanation to this audience. And secondly, I would say it enjoys something that a regular CFD might not have. First of all, is that I would really emphasize is the analog of particle dynamics in discrete space-time, at least in the original LGA spirit. All right, and because of that, it really had these set of features. And the third one is more practical, that at least in the original form, lattice Boltzmann is the advection is 1-to-1. That does not have the numerical smearing, and that is impossible for Navier-Stokes based to have. And because of that, it's a simple time explicit and highly transient that allows for a better simulation of a turbulent flow, including large eddy simulation. So that is a good segue to the later theoretical part of my presentation. So now I'm turning to aerospace. Lattice Boltzmann, one of the limitations in the early version is the Mach number limitation. So we have to really increase the Mach number. And recently, I'm glad that many groups have been really making a lot of advancements on this. This is talk about the high lift. Is one of the unsolved problems. I mean, there are also some other things.
Traditional fluid simulation tools struggle with these configurations. Difficult tests are still standard. This leads to expensive and time-consuming development, delays in flight certification, and increase the cost and risk in developing future concepts. But simulated fluid solutions offer a breakthrough in accurately predicting the highly complex and unstable phenomena that determine aircraft characteristics for all of these situations. Of particular importance is the ability to understand how airflow over the wing breaks down at very high angles of attack. Simulated fluid solutions are able to assess the impact of extremely complex geometric details on flow behavior, the influence of the jet engine on a high lift system, and buffet onset at high speeds, allowing you to predict stall with proven accuracy. Simulated fluid solutions on the 3D experience platform allow you to develop digital prototypes through virtual testing of real-world designs. By coupling dynamic loading between fluids and structural simulations, you can assess the impact of component deflections on aerodynamics, greatly improving and strengthening the design. Simulated fluid solutions allow you to augment and often replace physical tests. You can also receive insights into flow behavior that are simply not possible for physical testing. In the end, you'll be able to reduce development and certification risks, prototyping costs, and time to market, all while providing optimal aerodynamics and establishing greater confidence in overall performance.
All right. One of the problems is the how to predict the flow separation on an airplane when it is at a high lift position, and this is one of the challenging issues in the aerospace. So there has been a workshop on this, referred to as a Vision 2030. So the workshop is the NASA provide real tests and then invite world CFD groups to participate to submit their numerical results. And the submission of the results has to be compared blindly to the physical test results. And that has been going on, still ongoing. And one thing I want to mention is this is an experimental measurement. I mean, there are many other measurements, the pressure distribution and so on. But I just want to show something that shows the flow separation. This is like oil flow on the surface of a wing. And from this, you can see that these onset of the separation have happened on the base of the airfoil, at the junction between the airfoil, the wing and the body. And then if you have used the traditional RANS model, and you will find these are two representative RANS model based software, that they actually shows the separation start behind the engine, which is wrong. All right, and then you can also perform lattice Boltzmann with a RANS. I mean, URANS means unsteady RANS. You show the same thing. it shows the flow start to separate behind the engine. And only if you have the LBM combined with the proper turbulence modeling, you will be able to capture this this correct flow separation phenomenon. And so the thing is, when we submit it, we don't believe in URAS. So we use LBM plus DLES, and that's the results we submitted to NASA. And we did not know beforehand the experimental results. So that turned out that we are one of the, if not the only one, that actually gave the correct prediction. That was quite an important achievement. So now I switch gears to talk about turbulence. It has been almost 100 years, if only 50 years at least, that you know, we know the turbulence simulation cannot be done directly numerically by the existing computer or even foreseeable computers. So has been a field of important study in the physics that you know, we had to somehow only calculate the average behavior of turbulence. Unfortunately, turbulence is a highly nonlinear and highly, you know, highly chaotic. Therefore, I mean, people have great confidence on the validity of the Navier-Stokes, at least for the regular flow regime. All right, and so they started off by averaging the Navier-Stokes equation. All right, so but when you average the equation, you find that there is additional term up here, and that is the well-known Reynolds stress term. And okay, so the question has been, how do we represent this Reynolds stress term in terms of averaged quantities? That's the famous or infamous closure problem. All right, and then now let's look at the Reynolds stress term. Okay, so for many years, or even till this day, the Reynolds stress term, most popular approximation is by the so-called Busnesque approximation. It has this form. So the form actually, for people who know a lot about the, you know, the kinetic theory, and this form is really analogous to what it come out from the derivation of the molecular dynamics to Navier-Stokes. So the K is the diagonal term of this Reynolds stress term, and the off-diagonal term is the average rate of strain tensor. And so the assumption is the eddies behave like molecules, and they kind of provide this viscous effect and you know, the pressure effect. However, we know that's a very crude assumption, that if you know the eddy distribution in the Waves number space, you find this distribution is very continuous. So there is no separation of scale, unlike molecules to flow, all right, in kinetic theory, regular kinetic theory. So, and if you do some kind of a hand waving estimation, you will find the mean free path according to this analysis is about Nusselt number is about 0.1 to 1. Therefore, it is more like a finite Nusselt flow for the average turbulence. This is a bit how do I say, controversial, that Navier-Stokes is not a Nusselt not a Newton flow. However, the average Navier-Stokes behave like a Newton flow. I mean, actually, you think a little bit more, you think this is not a controversial, but if you just not thinking too much, you might think that's the case. All right. So, and there are some experimental support of that. I mean, this is like a pipe flow. This is not a small pipe. It's a regular big pipe, highly turbulent flow, fully developed turbulent flow. And you will find that the flow is not just unidirectional, but it has also this secondary flow pattern. And that's quite a characteristic of a Newton flow. And that's the average turbulent flow phenomena. Second one is when you have a sudden shear applied to a turbulent shear flow, and then you'll find the growth of the turbulent kinetic energy is not according to the regular eddy viscosity modeling. It actually it dips, it has a delay. Therefore, the energy actually first goes down before it rises because of the viscous dissipation. So this is another support of an average turbulent flow is a Newton flow. Third one is a representative channel flow. As we know, the channel flow, as you increase turbulent Reynolds number, and you will find the profile start to change from a parabolic profile and gradually flattens. First of all, is a flattening so that it is a deviation from parabolic shape, but also there is a slip on the wall. Here, a turbulence never had a true slip, but the boundary layer, as you have the Reynolds number goes to infinity, boundary layer can be viewed as a zero thickness in the limit. Therefore, it's like a slip. So there are many turbulence models to accurately predict the channel flow behavior by having appropriate eddy viscosity. But this behavior is reproduced by a constant relaxation time in the BGK formulation, or something equivalent, so that you don't really need a sophisticated eddy viscosity to tune the profile to the proper shape. But it's actually the relaxation time can be a constant. Well, everything else adjusted because of the finite mean free path effect. So that led to years ago, about 20 years ago, that my great friend who has passed away sadly about 10 years ago, that we were thinking about why can't we restart understanding turbulence from averaging of the Boltzmann equation. Because the Boltzmann equation naturally include all the information, including Navier-Stokes, right? And it clearly it covers from a viscous regime to Newton regime and so on. So that is quite a reasonable thinking. However, when we take the average of that equation, we quickly run into an issue that the particles, because the kinetic theory, regular kinetic theory, is based on molecular motions, but the particles move very, very fast. So their motion, the speed is about the square root of temperature, which is a much, much bigger quantity, at least for near incompressible flow. All right. Much, much greater than the turbulent kinetic energy. And therefore, you are running into averaging of quantity T that cannot be easily eliminated. Because in the end, the turbulence should not depend on another dynamic quantity like temperature. It should only include the turbulent quantity itself, especially in the incompressible turbulent regime. All right. And if you have another then physical, a quantity that has some physical dimensions, it also screw up all the screening laws. Therefore, this turned into a no-go. And I'm not saying this is impossible, but at least we cannot see any way to circumvent. But the idea is, I think it is very, very important. So now there is a new way of thinking. Recently, we have thought, why can't we, instead of looking at the molecule motions, why can't we think of motions of the flow itself? So we could, put a representative points in the flow. These are like, fictitious molecules, but they are not a molecular motion. They are followed exactly according to Navier-Stokes flow. All right, so you have a discrete representation of these points in terms of F. All right, and when you have that motion, you can immediately, very trivially, derive an equation that looks exactly in the form of Common-Tovich equation, which is for people who studied plasma physics should know very well. So because it is exact for obeying the motion of the fluid flow, it has no collision term on the right hand side, and when you sum over this particle distribution function, you immediately get the desired flow properties, such as flow density, which is trivially for incompressible flow is 1, and flow velocity. All right, this flow velocity actually obeys the Navier-Stokes, but let me say more, a little bit more about that. So when you take the moment integral of the Common-Tovich, you'll find that it results in this equation, that the second equation. All right, and then you immediately see, since the forcing term or the acceleration term A is given by the pressure and the viscous term, and the pressure is also solved by the knowledge of the velocity field. Immediately you find this moment, velocity moment, obeys exactly the Navier-Stokes fluid equation, and this is constructed out of first principle. All right, and since we have this representation, now we could do some averaging from this point of view. So I have a Coulomb-Tovich equation that exactly obeys the Navier-Stokes. Now I can do an average over that to get an averaged turbulent flow behavior. All right, so now I take an average over this Coulomb-Tovich equation. So I got very easily, the capital F is the average distribution function. And then you have these average terms on the left-hand side, and there is also a term, fluctuation of the acceleration interacting with the fluctuation of the F. All right, and so on and so forth. But interestingly, the right-hand side, you can do easy calculation. You find that it satisfies the mass and momentum conservation. And that tells us it is very much a collision. And I'll say why it is like a collision more later. So interesting enough, the average the equation of the Coulomb-Tovich, it looks like Boltzmann equation. And the left-hand side also has an acceleration term, which is governed by the average, the pressure gradient, and average the flow velocity. Um, so now, yeah, so you have this effective Boltzmann equation, all right? And then you take a moment of that equation, you will find it also recover the averaged Reynolds averaged equation for the capital U. All right, and this Reynolds stress tensor, you'll find it is given by the moment integral of the capital F. And also the kinetic energy is a trace of this capital moment of capital F. And so it's interesting that now the kinetic energy plays a role of the temperature for regular molecules, but it's a turbulent kinetic energy. Well, the Reynolds stress now is completely determined as soon as you have knowledge of the capital F. And further on the comment, when you have the knowledge of a capital F by solving this equation, you actually not only you can calculate the second moment, which is the Reynolds stress, but you can calculate any nth moment. All right, as long as F is known. This is so it has far more information than the Reynolds stress would provide. Okay, now let's talk about the collision. And then we find that the form of the collision is that it is the interaction of the force with the distribution, fluctuation of distribution. That actually you can write it down in a because it's an average. Average is many fluctuations that together. So it is actually is a random walk in the momentum space. Small random walks in momentum space, and that is much more of a natural explanation of well, I'm ahead of myself. Again, here I'm saying it actually satisfies the conservation of mass and momentum, but also there's one twist is that it does not satisfy energy conservation because fluid flow itself does not conserve energy. It actually dissipates energy into heat. So it is actually not an energy conserved, but it has a leakage to real, kinetic motions, which is the heat, and is given by the turbulent dissipation. All right, and then it is now let's look at what this collision. I was saying it actually behaves like a random walk in the momentum space, and that naturally gave the explanation why the 1 point PDF of turbulent flow it has a Gaussian form. 1 point is a Gaussian form, and we in the past many people have postulated why the 1 point PDF is Gaussian. 2 points is not Gaussian, correct? But 1 point is Gaussian. Is because of central limit theorem. However, this gives a more of a dynamic support of why that is the case. All right, and then you can easily move into a moving frame with the average velocity. Then you give naturally the equilibrium distribution of a Boltzmann form. And now in inhomogeneous turbulence, the 1 point PDF is not Gaussian. All right, but the deviation from Gaussian is because of the inhomogeneity. But for homogeneous turbulence, the 1 point PDF is Gaussian. Therefore, there might be a mechanism that actually, when you have a shear that pull the system out of the equilibrium, but the equilibrium is Gaussian. So there is a process. You could do a explicit random walk, or you can just use a model. Here, let's say we use a model such as BGK that we believe the distribution for homogeneous turbulence is a Gaussian. And we have a relaxation to this Gaussian equilibrium distribution. And with a relaxation time, which is unspecified. So this is an unclosed problem. All right. But at least let's say we believe this process is true. So there is a relaxation with an unspecified time to a local equilibrium. All right. Now, let's look at suppose we have solved this averaged Boltzmann equation. I mean the effective Boltzmann equation. Now we get the Reynolds stress. All right. And now, even though the Boltzmann equation does not need, you know, a Newton expansion, but then let's look to the Newton expansion to see what we can learn about it. All right. So when we perform the Newton expansion, and then we will find that, okay, after the Newton expansion, you can calculate the Reynolds stress according to the expanded distribution functions around the, you know, equilibrium, as I have described. So you will find that the zeroth order, this is actually is almost like a trivial repetition of what we do for molecular kinetic theory, right? So you have a Euler order, and now give rise to the two-thirds of a k times the delta function, and k plays a role of temperature. And then you look at the first order, you find now it has this form. The Vittorial part of the Reynolds stress is eddy viscosity times the average rate of strain tensor. And the eddy viscosity has this form of tau term, which is an unspecified parameter, times k, the turbulence kinetic energy. So this is really as what the conventional turbulence guys have postulated. All right, but since we are doing with kinetic theory, so we don't need to stop at the Navier-Stokes order, right? We can go beyond. So we can carry out the straightforward expansion to look at the second order. And actually, it is a combination of all these so-called secondary invariants. All right, and it has two interesting terms. The first term is a dt term, which responsible to the delay phenomena that we have seen earlier in the example of the turbulent rapid distortion delay, and with a delay time of tau again, and also there's the second order terms, the SS and S omega term, and these are responsible for the secondary flow phenomena in the channel flow. All right, and now there is one way to try to close the system to try to specify what the value of tau is. So recently we have approached this understanding. I mean, this tau, the determination of tau, will determine the famous C mu factor in the conventional turbulence modeling. All right, and since we have a kinetic theory, we can apply fluctuation dissipation theorem to estimate this tau. So it turned out this tau estimation gave the turbulent parameter C mu to be 0.816. Well, compared to the standard capsule model, C mu is 0.9, and the RG-based turbulence model, C mu is 0.0845. Well, we know that the standard capsule model and RG-based, the standard is empirically based on matching some typical benchmark flows, and the RG also has some assumptions made. So it is surprisingly close in terms of values, and And then from there, we can also further confirm what is the corresponding Knudsen number of this of the average turbulence. We found it indeed is around 0.1. That further confirm average turbulent flow is behaving like a finite Knudsen flow. Okay, and also we can use that quantity to compare to the second order turbulence, nonlinear turbulence model, the second order turbulence model. And there's several, I mean, three most representative turbulence models. And that give they have these parameters. They are empirically based or some kind of approximation. But ours is given below, and is also is very close. And they actually, you see, they are different models. They can even switch the sign. But it's interesting that we have one parameter, which is the tau, that give rise all of these unspecified parameters in turbulence modeling. So now I get to my conclusion. Engineering application deal with simulation of large-scale averaged inhomogeneous turbulent flows involving boundary conditions, as I demonstrated in the real world, application to real world engineering. And anti-viscosity-based closure modeling is mostly empirical and inadequate, as we all know about it. It is based on an analogy to a molecular system near local equilibrium. Average turbulence resembles flows of finite Knudsen number due to lack of scale separation and a greater departure from equilibrium. Starting from averaging the molecular Boltzmann equation is fundamentally challenging, if not impossible. A kinetic representation is constructed from a first principles rather than an analogy from based on what I just described, from a Clawich concept, viable for arbitrary deep non-equilibrium regimes. Reynolds stress and all higher order one-point moments are fully determined from a solution of the average kinetic equation. One parameter expansion in Knudsen number to first order recovers the most popular eddy viscous models, and to second order compare well with the well-known nonlinear Rez models. Closure is obtained by determining the relaxation time via a fluctuation dissipation relationship, purely within the kinetic theoretical framework, while such a value is determined semi-empirically in conventional turbulence modeling. So this is something I present to this audience because this audience is most familiar with kinetic theory. I mean, one of the audiences most familiar with kinetic theory. And I just want to give a bit of motivation. This is only a beginning. Many things can be done. I'm sure there are a lot of refinements or even revisions and so on. But through the years, I always believe kinetic theory for turbulence seems more appropriate and maybe more fundamental. To have all these unknown parameters in turbulence modeling to be determined by one underlying more fundamental quantity. Here is just one parameter, is a tau, the relaxation time tau. But it may be more than just one tau, especially for incompressible flow. I mean, for non-incompressible flow. So that's the end of my talk.
Thank you. Yeah, very interesting. Since now the kinetic energy takes the place of the temperature, do you get into any trouble if there actually is no turbulent kinetic energy? Because this would imply that the temperature would be zero.
What do you mean temperature is zero?
But no, you say that instead of the temperature,
Yeah.
the place of the temperature is taken by the turbulent kinetic energy.
Yes,
So then in a flow that has no turbulent kinetic energy,
oh, like a laminar flow.
yes, so that
Okay.
would be like as if in the kinetic theory, the temperature would be zero. And
In that region, yeah, it is, could be, because when you have a laminar flow, turbulent kinetic energy, I mean, strictly speaking, can be zero or near zero, right? But then the right-hand side, the collision operator is also zero. So you are dealing with the Common-Taubich equation itself. You don't need to average it because the average becomes kind of undefined, right? Unless you say, oh, I have an ensemble of laminar flows, then you have like turbulent kinetic energy, but it's not the turbulent kinetic energy. It's just the variation of ensemble of an laminar flow.
so does your model get into trouble if you?
It's not a trouble. We have to think about it, how to think about a laminar regime. But here I'm dealing with fully developed turbulence. All of these turbulence models are viable for fully developed turbulence.
Okay, thank you.
Thank you for the interesting talk. So it's interesting how you do the longer actually of the kinetic level. My question is, how one is that is first principle, because in the end you have your kinetic equation, but it's like you plug in yourself at some point, and then you do the filtering.
Yeah, it's not a plug-in the Navier-Stokes. It recovers Navier-Stokes.
Yeah, but you use yourself at some point to do
Yeah.
the acceleration.
The assumption is that
Yes.
the particle movements exactly obey Navier-Stokes. All right, they are not a free particle like kinetic theory. They are exactly follow Navier-Stokes. All right, so when you take a moment, you confirm that exactly recovers Navier-Stokes in the flow moment.
Yeah, but
Yeah.
how you use Navier-Stokes in your kinetic equation, and then you justify somehow that, yeah, we can represent like the turbulence model like fictitious tau turbulence, which is I don't know. I mean, there are already some works that shows that it's not exactly equivalent now than to the and of course you're showing that it's not. But I was a little bit confused by this mixing of levels because.
Okay,
Yeah.
thank you.
I don't know if you
Yeah, it's a kind of confusing, but you first construct the equivalent to Navier-Stokes exactly, but then you have a representation from a kinetic theory point of view exactly, which exactly recovered Navier-Stokes. Now the averaging over that, it has a different effect as averaging over the Navier-Stokes. So then these two start to deviate because when you average the kinetic equation, you get a Boltzmann equation, which carries far more information, including in the Newton regime, which we are worried about here. All right. And when you average Navier-Stokes, you don't have this information. You have to do some modeling, that basically borrows some kinetic theory concept, but it's more analogy rather than coming from bottom up, a first principle. That's my point.